Let's have a look at this rotational question. There's a couple of stages that we want to deal with. Part A, fairly straightforward. You're just finding the rotational inertia of the rod and the block. And basically with that one, you guys know how to do that by now. You're just summing up all the masses times r squared, where r is the distance from the center of rotation. And if you read the question carefully, we've got the pulley has negligible rotational inertia. The masses are very large compared to the actual rod, etc. So it's just point masses. You're considering these two masses as point masses. They're a distance of L away from the center of rotation. So I haven't heard anybody that's had too much trouble with part A. Part B, though, we've got to set it up. So we've got to switch to our dynamics mode. So when we do dynamics, we've got our rotational dynamics, which is torques. So if I look at where the object is rotating right in here and look at like a top view, the rope attached to the outside of that little rod, like that. So that's that rope right there, and that's our top view. It's creating a torque. So this tension acting on this string or this rope is creating a torque. So the torque, which is force times distance, will be our force of tension, and the distance would be just the radius of that rod, which they're calling little r. Now we also know that torque is I times alpha. And alpha is related to the linear acceleration or the tangential acceleration. So this rotational acceleration, which we're calling alpha in radians per second squared, is related to the tangential acceleration at this point, A tangential, by saying that it's alpha times r. So alpha times r is A tangential. So if I rewrite my expression in terms of linear terms, I get I times A tangential over r. So there, I'll call that equation 1. That's our rotational equation. Equation 2, I'll do in red. We'll look at that hanging mass. So for the hanging mass, we use our free body diagram, and I get a force of gravity down, which is just mg, but my mass is 4m. So it's 4m times g, and same rope, same tension up. Now, it wouldn't be the same tension if we were including the inertia or rotational inertia of this little pulley, but it says we're to ignore that, so we're all good. So we know it's accelerating down. Its acceleration will be the same as this tangential acceleration in this expression above. So I get ma, but m is 4m, equals mg minus ft. So there's my expression. We'll call that equation number 2. I'm just going to back off my pen here. It just seems a little bit too thick. Okay, so the idea is we want to sub equation 1 into equation 2. So the common term there is ft. So if I take equation 1 and I solve it for ft, I get ft equals I A over r squared. And then whenever I get an ft in equation 2 up here, I'm going to plug in an IA over r squared. So equation 2 becomes 4m times A equals 4mg minus IA over r squared. Now, the question in part B is what is the acceleration? So we got to get all our A's to one side, and we can do some factoring. I'll leave it to you guys to do the math, but I get A brackets 4m plus I over r squared equals 4mg. And then we solve for A. Now don't forget I was 2ml squared. And then the rest is just algebra. So the bottom needs a common denominator of r squared. You'll notice there's an m I can factor out right away. So since there's an m in every single term, I could factor out an m from the bottom, and that would cancel with the m from the top. So let me do that. And then if I get my common denominator in the bottom of r squared, my equation ends up looking like this: 4g all over 4r squared plus 2l squared all over r squared, which is the same as 4gr squared all over 4r squared plus 2l squared. Factor out a 2 out of the bottom, and you should get their answer right here. Now, when the large block, this 4m mass, has descended a distance d, how does the instantaneous total kinetic energy of the 3 blocks compare? So when they're talking about energy, then obviously it's probably beneficial for us to switch to energy mode. The initial energy of the system is just potential. This is the object that wants to fall. And apparently it's going to fall a distance d. So if we keep the lowest point of our problem ground 0, my initial energy is all potential. So my energy before is just potential, and it will equal 4m, g, and h is d. So all I've done there is I've said potential energy is mgh, my mass is 4m, and h is d. So that's my initial energy. Now, just before the block hits, what kind of energy have I got? Well, it's no longer got potential, it's got kinetic, and then this thing's also rotating, so it's got rotational kinetic energy. Point is, all it's got at the end is kinetic energy. All of this potential gets converted to kinetic energy. So the final instantaneous total kinetic energy of the 3 blocks should be equal. And you can justify it by talking about conservation of energy. And then I believe the next question, these masses are attached to springs or strings or something like that, and they end up lifting up. The bottom line there is, as soon as they start to spin and lift, you're also generating not only kinetic energy, but because you're raising them up slightly, you're giving them a little bit of potential energy. So you can answer that question accordingly as long as you remember you've got a little bit of potential energy in there. Okay, let me know if that suffices for a description.